Alright, so in this video we'll take a look at how do we work with Laplace inverse. I kind of briefly talked about in my previous video. So in this video let's take a look at that. So as I said earlier, it's a Laplace inverse transformation, so we are doing backwards, right? So what do we mean by backwards? For example, we know that Laplace of 1, the function 1, is equal to 1 over s. So what is the Laplace inverse of 1 over s, right? That will be 1. So if you have function 1, right, when you do the Laplace, then you get 1 over s squared, right? So then the Laplace inverse is backwards. So when you do the Laplace inverse of 1 over s squared, you're going to have 1 back again, right? Like a derivative antiderivative kind of thing, right? So that is the idea behind that, right? And similarly, for example, if you have t, when you do the Laplace, you get, I'm sorry, I think I made a mistake in here. This is supposed to be 1 over s. If you do the Laplace on the t, you have 1 over s squared. And then when you do the Laplace inverse of 1 over s squared, you're going to have t back again, right? That is the idea behind that, and that's what this kind of says. So a couple of things on the notations in here. So we know that when you have a function small f of t, when you do the Laplace, you get a cap f of s, right? When you do the Laplace transformation, you get a cap f of s. So what do? We usually do the Laplace inverse of the cap f of s. So I'm going to say LIT, Laplace inverse, or if you want to say, L inverse. What you get is you get a small f of t back again. Small f of t back again. So that will be a function of t, right? So remember that when you work with these functions, and especially with the notations. All right, so having talked about the notations, right, now let's take a look at some of the, again, basic things. Laplace inverse of 1 over s is 1, and Laplace inverse of 1 over s squared, the function 1 over s squared is t, and similarly the Laplace inverse of 1 over s minus 3 would be e to the negative 3t. So there are, you need to be a little bit careful in working with them. You will see it in a moment. What do I mean by that, right? So let's take a look at the, you need to be careful in terms of how do you work with constants, right? You have to be a little bit careful over there. So let's take a look at some of these formulas and then see how do we work with that. So as I said, Laplace inverse of 1 over s is 1, and Laplace inverse of n factorial over s to the n plus 1 is t to the n. So I want you to pay close attention here. And similarly, Laplace inverse of 1 over s minus a is e to the at. Laplace inverse of k over s squared plus k squared is sine kt. And Laplace inverse of k over s squared minus k squared is sine hyperbolic kt. And s over s squared plus k squared, if you do the Laplace inverse, it will give you cosine kt. And the Laplace inverse of s over s squared minus k squared would give you cosine hyperbolic kt. But I want you to pay close attention to this, right? Again, the good news is this is also the good news with this one is this is also a linear transformation. So a lot of things would work for us nicely, right? We'll talk about in a moment linear transformation. But for our purposes, right? What is the Laplace inverse of 2 over s cubed? And that we know, it looks like, 2 factorial over s to the 2 plus 1. So when I do the reverse back, my n is going to be 2. So the answer you're going to say this is simply t squared, and that's okay, right? But what if I give you Laplace inverse of 1 over s cubed? Then what do you do? So here's where the tricky part comes in. This is a very simple example. You're going to see things gets challenging as we move forward. Now you don't have a 2 factorial there, right? So what you're going to do, you're going to multiply 2 factorial and divide 2 factorial. Because of the linearity, what you can do is you can just put this 2 factorial inside, right? And then you keep this one outside. And now this is going to be 1 over 2 factorial is 1 over 2, and this will be t squared, right? And this will be t squared. So you're going to be on many of those things, you're going to be keep on working with those. Similarly for the sine hyperbolic kt as well. For example, if I ask you what is the Laplace inverse of, let's just say, 1 over s squared plus 25. I have a 25. The numerator is supposed to be a 5, but I don't have a 5 over there. So we don't have 5 right here. We're supposed to have a 5 there, right? To plug this into the formula, because it's a k. This is the k squared and this is the k, right? And we don't have that. Since we don't have that, now what we are going to do is, we need to have a 5 over here, right? So to do that, what we are going to do, we are going to multiply 5, and then we're also going to divide by 5, and so therefore we can say that is going to be 1 over 5 times sine 5t, right? We can do that. So therefore, if you ask me, if you summarize what I just did, if you ask me, what we have over there is, so if you ask me what is the Laplace inverse of 1 over s squared plus 25, and you have to do this adjustment with respect to the constant, that is going to give you 1 over 5 sine 5t. So you're going to keep on work with these things, especially when you deal with inverses. So all right, now let's take a look at some examples. As I said, these are very simple examples. 1 over s squared is simple, that is simply t, and 1 over s squared plus 4. If I had a 2 here, if I have a 4, if I'm going to have a constant, on the numerator, right? The constant I want it to be 2, but I don't have a 2. So what do? I am going to multiply and divide by 2. I'm going to multiply and I'm going to divide by 2. Because of the linearity, I can pull it outside. So I have a 2 over s squared plus 4. And this one, I can apply the formula. I can apply the formula right here. I can apply this particular formula right there, right here. And my k is 2 and k squared is 4. So when I do that, then I'm going to have, as you see, I am going to have the following, which is 1 over 2 sine 2t, right? And that's how we do that. The good news, as I said earlier, and that's how we will work with all these things. The good news, as I said earlier, it's a Laplace inverse transform is also a linear transformation. What do I mean by that? Laplace inverse of alpha f of s plus beta g of s is equal to alpha Laplace inverse of f of s plus beta Laplace inverse of g of s, which you can say alpha f of t, beta g of t. Remember, the way that we said was that for the Laplace inverse, you feed in capital F of s, and then you get a small f of t as the output, right? So you get that. Now, how do I use this linearity property to find something like this? Let's see, how do we do that? So now what I'm going to again use the linearity property and do it. We'll talk about something called partial fractions in a moment, but let's take a look at just this. This is a very simple one. You don't have to really use the partial fractions. So what I'm going to do, I'm going to rewrite this as Laplace inverse of 3s over s squared plus 9 minus 18 over s squared plus 9, right? Then what I'm going to, I'm taking a look at this formula right here, and looks like the denominator seems to be s squared plus 9. So s squared plus 9, and the first one I have a s, the second one I have a constant, right? So since it's the plus in the denominator, it's going to be either sine kt and cosine kt. The first one I have the s, so it's going to be cosine. The second one I have a constant, so it's going to be the sine, right? So that's the formula right there. So let's see how do we do that. All right, so therefore what I'm going to do here is I'm going to rewrite this as Laplace inverse of s over s squared plus 9. Thanks to the linearity, I can pull out this 3 outside. When I do that, I'm going to have a 3 over here, right? And then minus, this is where I need to be careful. I have 9 here, right? So which means I want the square root of 9 over there. I want the 3 here, but I don't have a 3, but I have 18. So what I'm going to do, I am going to rewrite this 18 as 6 times 3. So I'm going to keep the 3 here. I'm going to pull out the 6. I'm going to pull out the 6 outside. So when I do that, then this would be 6 times Laplace inverse of 3 over s squared plus 9. And now this fits into this formula right here. This fits into this formula right there. Right, so just in case, let me just copy this for you so you can kind of see it. Right, so because of this formula right here, right, we're going to apply this formula, we're going to apply over here, and we're going to apply this formula over there. When I do that, what I'm going to get here is I'm going to have 3 times cosine 3t, and I'm going to have negative 6 times sine 3t, right? And that's the answer for this. Again, thanks to this linearity property that makes our life much easy in terms of working with that. So now how do we work with this? Yes, we can use the linearity property, but the problem is the denominator doesn't look like one of the things that we know, one of the things that we have already there, right? It doesn't look like one of these, one of these, or one of these, or one of these, or one of these, or one of these. Then this is where we are going to use what we call partial fractions. So partial fractions plays a vital role whenever you work with Laplace inverse transforms. So how do you do that? So we are going to use a partial fraction to find these things, and the partial fraction for this would be let's take a look, right? So again, you all know that if you remember, let me quickly do the partial fraction on this one, but I let you do the other one on your own. So if you take a look at this one, just this guy, right, just this guy, I'm going to rewrite this into something. You would agree with me that I have a 3s plus 2 over s squared plus s can be rewritten as 3s plus 2 over s times s plus 1, right? You can do it like that. And now if you remember the partial fractions, right, partial fractions, and this is going to be a over s plus b over s plus 1, right? And then we solve for these a's and b's, right? Let me quickly do this for this particular problem, but again, I'll let you do this for other things on your own. So when I do that, I'm going to multiply the usual ways. We're going to multiply this throughout this on this side and that side. When I do that, then this is left hand side is going to be simply 3s plus 2, and the right hand side is going to be a times as plus 1 plus b times the s. And then what you're going to have is, there are a couple of ways to do. You can plug in the values of s, and then appropriately one of them will go away, vanish, and so on. Or you can compare the coefficients of the s and then constants and so on. You can work with either way. So here I'm going to plug in values so that you can find it easily here. So I'm going to plug in s equal to 0. When I plug in s equal to 0, the left hand side is simply going to be 2. The right hand side is going to be a times 0 plus 1 plus b times 0, and therefore the right hand side is simply going to be a plus b times 0, and that tells you right away your a is equal to 2. And similarly, if I plug in s is equal to minus 1, the right hand side, right, the left hand side is going to be this one, right? If I plug in that, the left hand side is going to be 3 times minus 1 is minus 3 plus 2 is equal to a times minus 1 plus 1, right, plus b times the minus 1, and that tells you that minus 1 is equal to minus b, and that tells you your b is equal to positive 1. So now if I plug these values back in, if I plug in a is equal to 2 and b is equal to 1 over here and here, you would agree that I'm going to have this one can now be rewritten as 2 over s plus 1 over s plus 1, right? And so therefore, ladies and gentlemen, now this whole thing can now be rewritten as the following, which is Laplace inverse of 2 over s plus 1 over s plus 1, which is going to be Laplace, again using the linearity property, Laplace of 2 over inverse of 2 over s plus Laplace inverse of 1 over s plus 1. And again, if we apply the Laplace in here, you're going to see that if we apply the Laplace in here, and again, if you apply the linearity property in here, the 2 I can pull it out. 1 is there, so it's not a big deal. So this will simply become 2 times 1, and this will become e to the negative t. So the answer here would be 2 plus e to the negative t. So therefore, the Laplace inverse of 3s plus 2 over s squared plus s would be that. Again, here we use the Laplace. Here we use the Laplace inverse. Here we use the partial fractions to find the Laplace inverse. If you ask me, when would you use that? When the denominator doesn't look like one of the things that we already have in them, right? Doesn't look like one of these things, then we would use the Laplace inverse, the partial fraction there to solve them. So here is another one. Again, I'm not going to solve it, the Laplace transform, but I'm going to give you what the Laplace transform for this would be, and then I'll let you work it out on your own. I'll let you work out the Laplace inverse on your own. But let me show you how once you do the I will let you work out the partial fractions on your own. But let me show you once we do the partial fractions how this will be changed. So for this one, if I do the Laplace partial fractions, right? So let me write it down. So if I have s plus 3 over s squared minus s times the s plus 2, and if I rewrite it, ladies and gentlemen, this will be s plus 3 over s times s minus 1 times the s plus 2. And you can work out the Laplace partial fractions. If you do them, keep on saying Laplace for partial fractions. If you do the partial fractions, and this will become negative 3 over 2 times 1 over s, and plus 4 over 3 times 1 over s minus 1, and then you're going to have a plus 1 over 6 times 1 over s plus 2. So you're going to have that. Now, so therefore, ladies and gentlemen, because of this reason, you can rewrite this. You can rewrite this as Laplace inverse of negative 3 over 2 times 1 over s plus 4 over 3 times 1 over s minus 1 plus 1 over 6 times 1 over s plus 2. This is not as simple as the one that we did earlier, by the way. The partial fraction, this is going to be a little bit tricky. The reason is, you have the constants a, b, c happens to be fractions, right? So you're gonna have to work with them. You have 3 constants. You're going to have 3 equations and 3 unknowns. So you're going to work with them, right? So if you use the partial fractions, that is what you're going to have. And then what you can do now, you can use the linearity property. And if you use the linearity property, then you can rewrite this as a negative 3/2 Laplace inverse of 1 over s, positive 4/3 Laplace inverse of 1 over s minus 1, and then 1 over 6 Laplace inverse of 1 over s plus 2. And if you apply the formula that we learned earlier, and this is going to give you negative 3 over 2 times 1 plus 4 over 3 times e to the t plus 1 over 6 times e to the negative 2t, right? So this corresponds to this, this corresponds to this, and this corresponds to that, right? That's what you're going to have over there. And that's how we would find the Laplace inverse of all that. So that's how you do the Laplace inverse. Now let's just do one simple, nice simple problem, right? Let's just do one simple applications of Laplace transforms. So to do that, I am going to introduce something called the Laplace transforms of derivatives, right? I'm going to do the Laplace transforms of derivatives. I'm going to introduce this formula, and then we're going to take a look at some examples, and then we will solve the solve an IVP. Let's solve an IVP using this Laplace transform and see how would that work. I will do this in the next video, so I will stop this video right here. In the next video, we'll take a look at the formulas dealing with the derivatives, and then how do you solve an IVP using the process that we outlined in the previous video, right? Let's take a look at the next video.